here we go. Introduction to the normal distribution. A sketch of a normal distribution resembles a bell, or bell shape. I feel like that's redundant to write the word shape again, but that's why I've written in my notes. Oh, it's a sketch. It's not redundant. A sketch of a normal distribution resembles a bell shape. It's also sometimes called a Gaussian distribution. From the mathematician named I think it's Frederick Gauss. He has his name all over the stuff in math and science. Anyway, that's not a commonly used term. It's a little bit of interesting historical information. Okay, so a normal distribution is one way that data can look. Is it the way that every data collection looks? No, it's not. It just fits a lot of stuff. There's a lot of data that fits a normal distribution. But the way that data is distributed helps us understand it. And when it does fit a normal distribution, it helps us to understand it even further by using standard deviations and such to figure out how far off people are from average, while people, whatever we're studying, are from average. Okay, so do you guys know of things where the data fits this pattern? Can you think of anything that might fit it, just off the top of your head?
Oh, done.
I have a bunch of ideas here that I got out of the video from our favorite video creator that we watch sometimes. The videos that came with the course. Any thoughts? Jenna? Like what? Sorry, masks make it hard to hear you. Yeah, so standard deviation is part of the bell curve. We're going to talk more about that because in here we have, like, right down the middle. So maybe you're confused about what actually makes this shape. So what it is you collect a bunch of data from something. And then when you put that data into, like, so we learned in a different unit of this class so far, we learned about, like, histograms, for example, bar graphs, right? If you put all of your data, like, in a histogram type of chart, and most of the data is in the middle, with less data on each side, for the lower numbers and the higher numbers, then you get a bell-shaped curve.
That was what I was thinking.
Yeah.
I was just trying to think of what it's probably called.
So what I'm asking for is data. Like, if you were to go do a survey, or if you were to collect data of some kind, what types of data do you think fit this graph? Yes, Joe. Heights? Probably. I bet it would. Well, just brainstorm some ideas. So you've got short people, and you've got tall people, and you've got average height people.
Weight?
Yeah. Perhaps heights, weights. I have written on here, as long as we're talking about, like, characteristics of people themselves, I've got, like, IQ scores. Not that this item has to do with IQ scores, but what about, like, ACT scores? We don't usually take the SAT around here because that's usually the one that schools on the East Coast want from you, but definitely you can't take the SAT. Here's some interesting ones that maybe you haven't thought of. The lifespan of a light bulb. You know, a package of light bulbs might say that a light bulb lasts an average of so many hours or something like that, right? But do some light bulbs feel like they die early and some last forever? So there's a very few that don't last very long, and a bunch that last longer than they really are projected to. And most of your light bulbs will stop working right around here. I don't know if that applies so much anymore because we've got all the LED light bulbs, and I don't know if that fits it at this point. Okay, now here's another interesting one. Kernels of corn popped. When popping microwave popcorn. What happens when you start popping a bag of microwave popcorn? Just get like pop, 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 right? So do you see how that kind of represents it? Number of pops over time, whole bunch in the middle, and then it slows down again. You're starting to get a feel for how this works. How the normal distribution, what the idea of it is. It can fit almost anything. And of course, there's things that it won't fit, but so time light of a light bulb. Any other brainstorms of things? I'm sure we'll see examples. We'll get to kind of get a feel for all sorts of different things that we could fit to this sort of model. Okay, let's look at a couple of examples. In a call center, the distribution of the number of phone calls answered each day by each of the 12 receptionists is bell-shaped and has a mean of 63 and a standard deviation of 3. Using the empirical rule, what is the approximate percentage of daily phone calls numbering between 60 and 66? Use the empirical rule. So we need to remember what the empirical rule is, right? Well, not remember, but learn it. Okay, I'm talking about myself. I need to remember what it is because I didn't actually explain it here in my paper. So we might have to go to our friendly neighborhood video creator. All right, so we were talking about the empirical rule, and the empirical rule is this rule that was discovered that shows that so the mean and the median and the mode are all right in the middle. We just call it the mean, but if a set of data really follows a normal distribution, then that mean, median, and mode are pretty much all the same, right in the middle. And then if we go one standard deviation away from the mean either direction, that encompasses 68% of the data. So 34% of it is above the mean up to one standard deviation, and 34% of it is below the mean to one standard deviation. So if you forgot what standard deviation is, we learned how to calculate it, and it just helps us know the spread of the data. And that's really, like with normal distributions, is where we're going to use that more than anything. So that was why it was important for us to learn it back in a previous unit, right? So then 95% of the data fits between two standard deviations of the mean. So 2 below, 2 above, that's going to fit 95%. And then 99.7% is between 3 below and 3 above. Now anything beyond 3 is kind of what we consider an outlier. It doesn't really fit. And that's a very, very low percentage of numbers that are outside of that, right? Okay, so that's called the empirical rule. Let's look at this example now. In a call center, the distribution of the number of phone calls answered each day by each of the 12 receptionists is bell-shaped, has a mean of 63 and a standard deviation of 3. So I've given you a basic normal distribution here, one that you could draw yourself next to any problem that you're doing. In the middle where the 0 is, that's the mean. And that means it's 0 standard deviations from the mean, because it is the mean, right? And where the 1 and -1 are, that's 1 standard deviation from the mean. And the 2's are 2 standard deviations from the mean, and the 3's are 3 standard deviations from the mean. Okay, so when we have a problem, so this fits anything, right? When we have a problem with specific data, we can now write in some of those numbers. So it has a mean of 63. So on our little graph here, we could write a 63 here for the mean. And it has a standard deviation of 3. So that means where the ones are, those are obtained by taking the mean and adding 3 and subtracting 3. So where the 1 is, what number would that be if I add the standard deviation to it? 66, correct? So I'm going to add 3 and I get 66 there. And for this one, I'm going to subtract 3. And so that gives me 60 at that spot right there. Okay, so using the empirical rule, what is the approximate percentage, because all of this is approximate, of daily phone calls numbering between 60 and 66? Okay, what did we just learn about the empirical rule? How much of the data is within one standard deviation of the mean? 68%, 34% above, right? This would be like 34% of the data and 34% below. And all together within one standard deviation of the mean this way or this way, total is approximately 68%. So about 68% of the phone calls will be between 60 and 66. Okay, now it doesn't matter what these numbers are. These numbers happen to be in the 60s, and our answer is also in the 60s. So those have nothing to do with each other. Every set of data has a mean and a standard deviation. And this rule, the 68, 95, 97.3, or whatever it was, 99.7, sorry, wasn't it? Is based on where those standard deviations land. Okay? Let's look at number 2. The scores of a midterm are normally distributed with a mean of 85% and a standard deviation of 6%. Find the percentage of the class that scored above and below the given score. So let's go ahead and start by labeling our bell curve here. So what goes here at 0? 85, that's the mean score on the test, right? Okay, what's the standard deviation? 6. So, for this first standard deviation mark here, we're going to add 6 to our 85, so that will be 91. To get back to this negative one, we're going to subtract 6. So 85 minus 6, that would be what, 79? Then we can keep going so that we have our chart completely filled in to answer the question. So what would be past 91? 97. I guess we could keep going, but I feel like if this is a percentage, that we're not going to probably have percentages over 100, but just follow the rule. So 97 plus 6.
103.
Yep. And we'll even have to use it. So, and then let's go backwards. So 79 minus 6, 73, and then 73 minus 6, 67. Okay. So I'll kind of squished together. All right, let's look at what we're trying to figure out. Find the percentage of the class that scored above and below the given score. Okay, so we want both above and below. So, students that scored above 91% would be in here. Well, here's some things to remember. Half of our bell curve, so half of our data, is on the right side of the mean, and half of our data is on the left side. So that means that 50% of our data is this direction, and another 50% of our data is this direction, right? Well, what do we know about the percentages specifically within these sections? If this entire thing here is 68, I already wrote them up there. What is this piece right here going to be? 34. Well, the entire thing is 50. This piece in the middle that I did not highlight because it is not above 91 is 34. How can you use the 50 half bar graph and the 34 from the empirical rule to find the yellow part? Subtract it, right? So above 91% would be 50 minus 34, which would be like, what is that, 16? So 16% of the class theoretically got above a 91%. Okay, what about below 91? Well, hopefully it makes sense that the entire graph represents 100% of the data. And so if above 91 is 16%, what's left over for below 91? 4. Okay, so we take 100% for the entire graph. We subtract out the 16% that's above, and we have 84% that's below 91%. All right, let's look at our score of 73. So that would be here. Go ahead and highlight this section this time, our little below piece. And then let's remember what our empirical rule numbers are. So this is 34. And then from here to here is 95% of the data, right? So what's half of 95%? 47.5. Okay. So this piece here represents 34. So how much more do we need in this piece to represent so that the 34 plus something is 47.5? Like 23.5? That sound right? Oh, 13.5. Yeah, 23. Sorry. 13.5 in there. Okay. So if this entire half bar graph is 50, and this piece in here is 47.5, is that what we said together? So 47.5, how do we find the section that's below? So this half of the graph is 50, and this piece is 47.5. So what's that purple piece going to be? I can take 50, subtract 47.5. About 2.5. So 2.5% of the class had scores less than 73. That's pretty good. That means most people passed, right? Because that's like a C. Okay, what about above? Oh, well, that's what I was just saying. Most people passed. So that's what this number is going to represent, is how many people got above that 73, that C value. So the entire graph is 100%, and below 73 is 2.5% of the data. So 97.5. All right, are you getting the hang of how to use this empirical rule to find the percent of the data? This also has to do with z-scores, which is like the next page, but we're not going to go that far today, because I need a few minutes to figure out what I want you to work on, what I want to add to your assignment, and there's many of you that still need to work on calculating stuff. So at this point, you've got a half hour of class. You're going to start working on whatever you need to work on while I figure out what your next assignment's going to be, and then I'll add them in.